Hello everyone, and today we'll be seeing one of the problem from Geeks for Geeks. It says sum of nodes in the BST range. The problem is simple. We are given a root of a binary search tree and two integers, L and R. The task is to find the sum of all nodes that lie between L and R, including L and R both. So this is a very typical question where we wanted to traverse a binary search tree, and this requires you to understand how binary search tree is. So binary search tree is just a tree where nodes are arranged in a particular fashion, which means for a node, its children left and right are in the way that the left child is lesser than the parent and the right child is greater than a parent, and it follows the subtree as well, like within the lower subtree. So this 12, for this 12, 8 is lesser and 20 is greater, and each for every 20 it should not go beyond 22 because 22 is the highest limit. So any of the node within the left hand side of a 22 would not exceed 22. That is how the binary search tree is designed. You can re-verify upon this. For more, I have attached a link upon how to iterate a binary search tree and how to validate if a tree is a binary search tree. The solution along with the code and explanation, you can find it over the link here. You can go ahead, and I highly recommend to check it out. For this question, we are not required to validate as such, but we are sure that it is a binary search tree, and we need to find a sum of all nodes that lie within this range. So range is something very sweet when we comes to binary search tree, because it doesn't require traversing each and every nodes. We already know uh, what is the range from left and right, and the maximum time complexity we can expect is the height of the tree, which is in ideal cases log n. So for this kind of question, the ideal thing or ideal time complexity should be O of log n. So how do I approach with this solution? Let's take an example. These are very tiny examples, so I would not go ahead with this. Uh, let's take an example in like this. So this is a binary search tree which I have provided, and we need to search within the range from 1 to 10. So we'll go ahead, start from this node. This is the root of a tree, and we are at this position right now. So as we know that for a binary search tree, it has its own order. So we wanted to get more than this element, we can go on right hand side. If we wanted to get lesser than this element, we can go on left hand side. So considering our range, it surely lies on the left hand side because the maximum number 10 is less than 25. So we need to go on the left hand side. Now we are no more here, but we are over here. So we have traversed this, and going ahead with this, 1 to 10, we are again expected to go on the left hand side because it's again lesser. Now 12, again the same story, both of these are lesser, so we are expected from here to go to this. So for 2, we wanted to go ahead and check whether we have this or not. Oh, wait a minute, this 10 should be on this side and it should be null here. Correct, that's the way. And for this 2, it's obviously is within this range, so we can consider this. So let's consider this, or take it as I'm considering this for a positive plus. Now we are going to left, but left is null here, so we just go ahead and come back to this node, and we see that, hey, can I go to right with the help of this range? And it says yes, you can go to right. And I'm going to right now. I'm taking that I'll see left and right of this node, but it doesn't have any left and right childs, So my final answer for this is 10 plus 2 is 12. Result is 12. See how the way we traversed is we used one by one route, and either we made a choice, either we can go on the left or right. That is one thing where we pruned the entire right subtree. So for 19, if we didn't have the right subtree in the case if say 24 and all the nodes beyond 24, the problem statement would still remain the same, our solution would still remain the same, and our tree, whatever we have traversed, would be look like this. It is a significant improvement from the earlier tree which we looked at. So we came from this tree to this tree, which is a very significant improvement, which into my opinion. So this is how we follow the time complexity of log n, and there are two ways. We can either go iteratively or recursively. Recursively is a clean and simple solution which uses a stack space, and for stack space taking stack space into consideration, it would go to log n. So with this kind of logic, we have our algorithm ready in a way that what we are trying to achieve is check the current and identify if it is within within range is lesser or range is greater. Obviously, if both of them won't satisfy, then this is the default. If both didn't satisfy, and within iteration, just go ahead and add up the data values of each node. Fair, simple. So let's go ahead with code first. I'll go ahead and check the classic check whether if my current root is equal to null, and if this is null, then I'll return 0 because obviously we don't have any value, so yeah, it's 0. Again, the terminal or ending nodes won't contribute anything, so this null would return 0. But let's check if these are within the range. What do we do? So these are within the range, that means our left is lesser than or equal to current, and current is lesser than or equal to right. And what is current, you may ask? I'll say that int current is equal to root dot data. So in this case, we are within the range. Now in this case, we go ahead and consider the node, consider the left and right as they might be within range as well. So return current plus, I'll go ahead with node sum of root dot left with same range because we are not going to alter the range, node sum of root dot right of L comma R. You may ask why I choose left or right, because it might happen that hey, our 2 is within the range, and it might happen that here is 7, it might happen that here is 5, here is 8. So it might happen within the 2 itself. Okay, 7 cannot be here because it's a binary search tree, my bad. Here's 1, and for that matter it's 1.5. I know it's not a double, but for the time being. So we don't want it to miss upon the opportunity that hey, I'm not choosing left, I'm not choosing right, but it might happen that I wanted to choose 2, 1, 1.5. I'll ignore 0.5 because it's out of the range, and I'll also include 10. In this case, we have included left and right. That's the reason I'm including left and right. If and only if my current range or current value is within the range. But there might be chances where my current is lesser than the range. That means current is way less. We need higher numbers. So for higher numbers we will go ahead and to the right hand side, because you know that the higher numbers mostly lies on the right hand side. You can see 30 and here as well 11, 20. So it's a BST. It will go to higher side. So we'll go ahead with root dot right, left, and the range which I have specified. Else return node sum of root dot left L comma R. So anyway, I haven't changed the range because the range they have provided, so we don't want to change this, so make it final. Anyways, this is a good refactoring change for this. So far so good, it looks nice. We have considered case 1, case 2 and case 3. I'll go ahead and I'll quickly run this program, compile this one to check for any compiler errors. Program compiles well, and I'll run this for rest of the test cases. I have covered most of the topics with the binary search tree as of now. You can go ahead and visit the video on your right, and I'll see you in the next one. Thank you.